Let's talk about halogen thermodynamics. Let's get started with getting specific about our first radical reaction. Notice here that we are going to be talking about thermodynamics. Thermodynamics is going to be very important for us to understand what is happening based off of our reaction. Now, halogenation, overall reaction here, is going to be a substitution. This substitution reaction involves substituting a hydrogen for a halogen. So notice we have CH4 here, just a very simple organic molecule. We are taking that CH4 and making it CH3X. Now, typically for halogens, we've worked with Cl2 and Br2. We are going to be doing the exact same thing here, but we want to make sure that we understand the difference between chlorine diatomic and bromine diatomic. Now, notice in this overall reaction that we have a couple of things going on. We have bonds breaking. We are going to be breaking the CH bond and the diatomic halogen bond. We are making a carbon to halogen bond and an H to halogen bond. So there is some enthalpy going on here, right? Delta H equals bonds broken minus bonds formed. The entropy term is going to be negligible for us. We don't really care about entropy here, because if we look at the actual reaction, we have two molecules making two molecules. So entropy is going to be 0. Now, when we look at the reaction itself, what I want to present here is the mechanism. We need an initiation, a couple propagations, and a termination. We're going to follow this cookie cutter type mechanism. It's a slight change of what we're used to. However, radical reactions are different in that their homolytic cleavage requires a different style of mechanism. The first thing that we need to be able to see is that homolytic cleavage. We'll see that the halogen bond, X2, is going to homolytically break. We do need heat or light, either one. HV is light. If you imagine energy equals H nu, delta is heat. We need one of these. They are our radical initiators. So X2 will not just homolytically cleave without a specific H nu, light, or delta, heat. Once we make that radical, we can go straight to our propagation steps. In the propagation step, we will start with hydrogen abstraction. A hydrogen off of our organic molecule will combine with the halogen. There makes that new bond, followed up with the formation of a radical on the carbon. This is hydrogen abstraction, because the halogen is taking the hydrogen away. The radical is taking the hydrogen. Next, we will have a second propagation step to make our second molecule, the actual organic product here, where we have halogen abstraction. The carbon radical will pair up with one of the halogens in a second equivalent of X2. This propagates and makes a second equivalent of halogen radical. So we are making a new bond and making a new radical in this halogen abstraction. That completes the two propagation steps for this reaction. So then we would wrap up this mechanism with a termination step. Any two radicals that you have seen in this mechanism, they could be carbon radicals or they could be halogen radicals, can come together in this coupling reaction. I'm choosing the halogens to come together because they are the simplest to write. And so why not make life a little bit easier for ourselves? Here is the overall mechanism for halogenation. Whether you are using Cl2 or Br2, the reaction mechanism is the exact same. We have to consider thermodynamics though, so that's what we're going to do next. Which one, chlorine or bromine, reacts faster? Which one's slower? Mechanistically, they are all the same. Kinetically, they are quite different. Here's some thermodynamics for us. This chart is a good explanation of bond breaking versus bond forming that we just talked about. We can estimate the delta H, the enthalpy term, based off of the bond dissociation energies. We know bonds broken minus bonds formed. Here are all of the different types of bonds relevant to this reaction in terms of bonds breaking, minus bonds formed. Don't worry, you don't have to do the math. It's done for you. So when we look at this, what we do notice is that using I2 is not enthalpically favorable. Enthalpy here as a positive, this is endothermic. That would relate to a non-spontaneous reaction. Remember, entropy term is 0. So whatever the enthalpy sign is, that's what your Gibbs free energy sign is as well. So endothermic means endergonic, means not going to happen. Gross. Now, F2. Yeah, you're like, why not, Lauren? Come on, let's go ahead and use this. This is way too anthropically favorable. There is no way that we're going to get F2 to react this way. We choose to use chlorine diatomic and bromine diatomic because they are our superstars. They are the right type of spontaneity that we can see without being catastrophic for the actual reaction. Notice though that their delta H's are different. Cl2 has a more negative enthalpy. It's more exothermic than the delta H for Br2. So both chlorine and bromine are exothermic, which is favored. But let's look at the big difference here, the difference between the first propagation step and the second propagation step. Let's remember our mechanism. Hydrogen abstraction, the halogen will come and make a new bond with hydrogen and make a new radical on carbon. Notice the difference here between chlorine being the radical that does this versus bromine being the radical that does this. What do you remember about bromine versus chlorine as anions? Well, we know that Br minus is more stable than Cl minus. The same goes here. Br radical is more stable. It's harder to react in hydrogen abstraction. And so that's some key point here to look at, that hydrogen abstraction for bromine is slower than that for chlorine. Chlorine's hydrogen abstraction is faster. It's exothermic. So we make more stable things. That's something interesting. We're going to look at the reaction coordinate diagrams in just a second. The second propagation step is very similar for both of them. Halogen abstraction, right? Making that new carbon to halogen bond. Look at these numbers, very, very similar. So when we're looking at the rate determining step, it must be that first propagation step. There's our rate determining step, hydrogen abstraction. This is the one that we want to focus on when understanding the difference between chlorination and bromination in this radical chapter. Bromination is much slower than chlorination. This means that bromination is going to be selective. That first step, the rate determining step, is either going to be for chlorine, exothermic, for bromine, endothermic. We know, same idea when we were forming carbocations. If that rate determining step is really slow, we get to be selective. We get to choose what reaction we are going to do. What this literally means is that when we start looking at the products coming out from chlorination versus bromination, chlorination is not going to be selective. It will do hydrogen abstraction on any hydrogen that we have. Bromine is going to be choosy. He's going to be selective. He's going to take his time and figure out which hydrogen is the best to remove. Which one is going to actually be the easiest to remove. Even though secondary radicals are more stable than primary, we see chlorination making multiple products. Not quite racemic mixtures, not 50-50, but definitely major versus minor, and getting multiple different constitutional isomers. And that big overarching reason is because in the rate determining step in the hydrogen abstraction, the transition state difference is very, very small. There is a small difference in energy here. And so either radical will technically form, right? Yes, the secondary carbon is faster than the primary, but what's of utmost importance to note is that chlorine is not selective. We will make more than one product. Chlorine can go on any position out of that organic molecule. Notice that we're only showing carbons 1 and 2 here because propane is symmetrical. Carbon 1 is the same as carbon 3, right? Taking that a little bit further, we see the same propane molecule and we see a 97% product from the secondary carbon. This can't isolate that. We're going to assume that that means it's not formed as an actual product. If I can't actually isolate it, if I can't extract it as an organic chemist, I'm not going to ever see it in my product solution, right? I'm not going to be able to isolate it as a viable product. So bromination is slower because hydrogen abstraction is endothermic. Chlorination is much faster and not selective because the rate determining step, the hydrogen abstraction, is exothermic. The Hammond postulate will be able to explain a little bit better for us. In the Hammond postulate, we said whatever molecule, the reactant or the intermediate, whichever one was closer to the transition state is what we want to focus on. So in chlorination, the transition state is closer to the reactants. And so what that means is that the bond of the carbon to the hydrogen is only beginning to break, not really broken yet. The energy cost is not quite there yet. So any hydrogen is valid to be abstracted. In bromination, the intermediate, the radical, is closer to the transition state in terms of energy. And so therefore, we assume that the bond is almost completely broken from the carbon to hydrogen. So the bromine has to be very selective at which hydrogen it's going to remove. It's going to remove the hydrogen that is on the more substituted center to result in the more stable radical. Chlorination does not do this. And so when we see chlorination, we'll get all different constitutional isomers on our alkane starting material. Bromination is going to be much more selective for the lowest energy pathway. That means he will choose a tertiary over a secondary, he'll choose a secondary over a primary, and he would choose a primary over a methyl. Let's look at that a little bit more in depth. We have two different positions here. We have a tertiary position, and all of these methyl at the end are going to be our primary positions. Notice how all of these are the same, right? We'll call this A versus B. I'm going to erase the other B's because I think that they are understood, that they are the exact same CH3 groups. For chlorination, yes, our major product will be on A, but we will also get B's, right? This reaction actually is about a 65% to a 35%. You don't need to know those percentages, but you do need to know how to draw all constitutional isomers possible. For bromination, we will only be drawing the more substituted position. We will not get the halogen Br on any of those outer primary positions, only the most substituted. So only the most stable carbon radical gets the bromine. You can think of chlorination as another Oprah reaction. You get a chlorine, you get a chlorine, you get a chlorine. Everybody gets a chlorine. All right, just a slight nod to stereochemistry. These reactions, whether it is halogenation with a chlorine or with a bromine, these reactions are not stereoselective, which means that when we have that carbon radical, we will be able to, in the hydrogen, the halogen abstraction, let's just draw that step. If we want to think about how that chlorine is being attached, I just chose the most substituted to start off. When we imagine that chiral center is formed, we will actually get a racemic mixture. Why? Because the carbon radical, we are going to assume in this class, is sp2 hybridized, trigonoplanar. So the radical could be up top, or the radical could be on the bottom, right? So when we have that hydrogen abstraction, we have two ways, top or bottom attack. So looking at our actual products here, we will make two secondary alkyl chlorides and one primary alkyl chloride. 3 products total.